Real-world machine learning applications require thorough evaluations to ensure their performance on critical data slices. For example, for autonomous driving, models are required to meet product requirements under different conditions of weather, distance, object types, and so on. Or for AI fairness, models are also needed to perform well over different social groups. We call such conditions or groups data slices. However, it is a non-trivial task to efficiently evaluate and improve model performance under all condition combinations. We have two main challenges. Challenge 1. Manually slicing the data is time-consuming and may miss critical data slices in the model. Challenge 2. Once a defect is found, it is risky and time-consuming to iteratively improve models without foreseeing the trade-offs between data slices. We propose SliceTeller, a novel data-driven AI framework for slice-based model analysis and model improvement. The slice finding algorithm automatically searches the validation dataset for human interpretable slices that can be explored with our visual analytics approach. Once critical data slices are identified, we invent a slice boosting method to estimate the performance trade-offs for prioritizing different slices. We can then iteratively optimize models over the critical data slices with different approaches, for example, data augmentation or sample weighting. The main component is the slice matrix, a representation that summarizes problematic data slices. In the slice matrix, rows represent data slices, and columns represent one-hot encoded slice descriptions. Slice metrics are shown for every data slice. When users select a data slice, data distributions are shown for both tabular and image data. Use case 1, Celeba. As a first example, we look at an image classification problem. Our goal is to identify potential bias issues. We trained a model to classify gray hair on the Celeba dataset and obtained an overall accuracy of 0.98. We use annotated binary attributes, such as gender, skin color, and smiling, to slice the data. After we easily import our tool into the Juniper notebook and inspect the model with SliceTeller, we notice a potential bias. As Slice 1 indicates, the model is failing to classify females with gray hair because of a small dataset size of this slice. We can further verify this observation by browsing the sample images in the MatrixScape view. The poor performance on Slice 2, with people not wearing neckties, also seems related to gender bias. We can estimate the effect of optimizing the model for Slice 1 and 2 together, noticing a positive effect on the worst 8 slices. Therefore, we decide to optimize the model over the biased slices 1 and 2 after verifying the estimated effects are desirable. After the optimization, the model's performance on the gray-haired female images is significantly improved, as well as other worse slices. A side-by-side comparison in the Tilescape view confirms the group DRO's performance classifying gray hair males and females has significantly improved. With our tool, we successfully mitigate the gender bias issue to classify gray hair. Use case 2, ultrasonic object classification. As a second example, we show how SliceTeller can be used to improve perception models for autonomous driving from a real business partner. The goal is to train a robust model to classify object heights, high or low, with ultrasonic sensor data. We trained an XGBoost model on the sensor data, obtaining an overall accuracy score of 0.88. The product requirement is to ensure the model is robust towards specific sensor and environmental conditions. Every data point has associated metadata, including object distance, object type, weather, and so on. We use the metadata to investigate the model with SliceTeller. Slice 1 is defined by sunny weather and high clutter. Slice 2 has high clutter and low speed, and the other two slices 7 and 10 have objects curbstone and container side. The what-if estimation shows that when optimizing the selected slices, they will be improved They retrain the model with the same parameters but more weights for the selected slices. This model too can indeed improve the performance on these slices. However, they see a trade-off on other slices, including slice 139, rain, slice 142, object wall. They found the trade-off on slice 139 not acceptable because the rain condition is critical for autonomous driving applications. In the next iteration, they also optimized the model for the slice rain and obtained a good trade-off across all slices. And now we successfully meet the product requirements of the detectors at this testing stage. They can then be passed for downstreaming tasks such as sensor fusion. In conclusion, we have shown how SliceTeller can help practitioners to evaluate, find defects, and improve their models with a novel data slice-driven approach. We believe our method and design process together with industry ML practitioners can benefit the practice and research of using visual analytics for model validation at large.